the fact that light doesn't travel particularly fast over cosmological distances, 186,000 miles a second. That means that as you look out to even nearby objects, let's say the closest object you can see with the naked eye, the Andromeda galaxy, if you look at that about 2 million light years away, it means you see it as it was 2 million years in the past. You look at more distant galaxies, 10 million light years away, 10 million years in the past, and so on. So you could ask the question, well, in that case, are there objects that are so distant that the light travelling from them began its journey close to the Big Bang itself? Is that possible? And the answer is yes. And that light was first detected in the 1960s. It's called the cosmic microwave background radiation. So essentially the idea is, how far can I look in every direction? You can look about 13.8 billion years into the past, back to the origin of the universe. It's on this diagram here. It says afterglow light pattern, 380,000 years after the Big Bang or so. That is the furthest we can see. We can't see further back than that because in earlier times the universe was so hot and so dense that it was in the form of what's known as a plasma. So essentially the atoms couldn't form. Temperature was too high for atoms to form. So you have electrons and primarily electrically charged protons and helium nuclei buzzing around in a thick soup, opaque to light. But at that moment, and it almost is a moment, cosmologically speaking, 380,000 years after the Big Bang, the universe is expanding and cooling, and it becomes cool enough for atoms to form, and becomes transparent almost in a moment. And so the light can journey across the universe ever since from that point, and we can detect it today. And that's what we call the cosmic microwave background. Here is the most recent photograph of that. So this is presented as a sphere because that's essentially what it is. It's a celestial sphere. So it's as far as you can look in every direction surrounding the Earth. And what you're looking at there is an almost featureless and formless universe. And the colours correspond to slightly different temperatures in the light, which are really telling you that there are regions which are very slightly denser than other regions in the early universe, but it's almost uniform to 1 part in 100,000. So we're seeing an almost uniform soup, no stars, no galaxies, no large structures in the universe at all, and that is telling us that the universe has not always been the same as it is today. It is not eternal in the sense that it's not always been around with galaxies and stars and planets. At this point in the past, which we can see in the photograph, there were no stars and no planets and no galaxies. The universe was a hot, dense plasma. And that is essentially the clinching piece of evidence, certainly when it was first seen in the 1960s, that told us that this theoretical prediction that the universe was once very hot and very dense was correct. It matches observation. The universe was hot and dense 13.8 billion years ago. Now, those fluctuations, the different colours, as I said, correspond to very slightly different densities in the early universe. What do they tell us? These are the seeds of the galaxies. So you stick this, essentially you can stick this into a computer simulation, evolve it forward in time, and you will see 13.8 billion years later a distribution of galaxies that matches statistically the distribution we see in the Sloan Digital Sky Survey. Again, so matching observation. So the question becomes, if these little overdense regions collapse to form the stars and galaxies, where did they come from? And this is where we start to probe theories back towards the Big Bang, and in a sense, theories of what may have happened before what we now call the hot Big Bang. So if we define the Big Bang as a time when the universe was very hot and dense, we have a theory which was pioneered by Stephen, amongst others, back in the 1980s, that tells us how, or predicts how, these small areas of different density could have formed. It's a theory called inflation. Before the universe got hot and dense, it was still there and it was doing something else. It was stretching very fast. It was doubling in size on very short time scales, actually around 10 to the minus 37 seconds, which as you write it out on a piece of paper, looks like this. That's why the theory is called inflation, by the way, because the thing is inflating very fast. The idea is that inflation is driven by the stuff that you put in the universe. This is central to Einstein's theory of general relativity. In this case, the stuff is something called an inflaton field. It's the kind of stuff that makes the universe stretch very fast. But what was developed actually here in Cambridge in the 1980s, particularly, was the idea that that smooth sort of ocean, if you like, a field filling space, is not entirely smooth. It can't be. It must have ripples in it. It's not really a still ocean of energy. It's like a stormy sea. And what that does for you when you calculate that is it tells you as that inflation draws to a close, as it must. The universe has to stop expanding at this rate and goes through the hot Big Bang. Then some pieces of space will be stretched a little bit more than others because of the ripples in the energy field that's driving the inflation. Some bits of the universe stop inflating a little bit earlier than others, in other words. That leads, when you dump the energy into space and heat it up and make particles, it leads to a slightly non-uniform distribution of particles in the space, which you can calculate from the theory. And when you do that, you find the pattern looks like this, our observation of the universe 380,000 years later. So that's the reason why inflation is, I would say, although there may be a few people who disagree, but I would say it's the most commonly accepted theory of how the universe came to look like that, which subsequently tells us how the universe looks like it does today.
There are stars that are literally the size of solar systems. The more massive the star is, a star, let's say 10,000 times the mass of the sun, then it has to burn its fuel extremely quickly to stay up against the force of gravity. So they're very, very, very short-lived, the really massive stars in the universe. I don't know the figure for the biggest star, but one of the biggest you can see with the naked eye actually is Betelgeuse or Betelgeuse in Orion. And what's interesting about that is if you put it where the Earth is, then it would extend out pretty much to the orbit of Jupiter, I think even beyond the orbit of Jupiter. So if you imagine how far it is to Jupiter, that would be orbiting inside the star. And it's so big that we can see sunspots on the surface with telescopes here on Earth. So it's a vast star. That's a star at the end of its life that's swollen up. That isn't, however, the biggest.
We say the universe began 13.8 billion years ago. That's a measurement. So because we can measure the speed that all the galaxies are flying away from us, essentially. You can run time backwards, if you like, to find out when they were all on top of each other. And so it's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been eternal. When I talk to people, some people get upset about that. Some people would rather it had a beginning. The idea that it might have been around forever is more frightening somehow than the fact that it began. What terrifies you the most, an eternal universe or a finite universe? If you look to the LHC, which is the Large Hadron Collider, which is the place where we generate the highest energies, so it's the biggest microscope in the world in that sense, we have an extremely good understanding of the laws of physics at that level, up to and including the discovery of the Higgs particle.
That's been proven? Is that end of debate at all?
There is a particle there that we've discovered, and it has all the right properties to be the predicted standard model Higgs particle.
Please explain what that means.
So the Higgs particle, it was predicted back in the 60s by Peter Higgs and others, and it's the idea is basically that early on in the expansion history of the universe, so let's say less than a billionth of a second after the Big Bang, as the universe cooled, it went through something condensed out into empty space. So people call it a phase transition, but it's analogous to a window pane on a cold winter's day. It's analogous to water vapor condensing out into ice. As you drop the temperature, it changes into something else, into ice. So in the same way that the theory is that as the universe cooled, something condensed out. So empty space isn't empty. It's full of Higgs particles, if you like, or a Higgs field. Wow. So this means this space. Now, it's not just space between the galaxies, it's in this room. That every square meter of this room is full of the Higgs field. And our fundamental particles, the electrons, let's say, in our bodies, interact with that Higgs field. And in that process, they acquire mass. So it's the mass generation mechanism. It's why some particles are massive, like electrons and quarks, and some things like photons are not massive. They're massless, and they travel through the universe at the speed of light. So that's the theory. Now, that was suggested and built mathematically, essentially. There was very little evidence for it at the time, back in the 60s. But over the years, the theory, called the standard model of particle physics, passed all experimental tests. So we got to the point where we thought, right, okay, we will build a machine that will either disprove or prove that theory. And the LHC is such a machine. If that theory is correct, which it now seems to be, the prediction is you must find the Higgs particle at the LHC, or some kind of Higgs particle. And indeed, we found it. There are 350 billion galaxies in the observable universe, so surely there are civilizations out there.
And more advanced as well, then.
Yeah, I'm sure that's the case.
Sure.
And it has to be the case in an infinite universe.
Yeah.
But if we confine ourselves to the Milky Way, which is really the only place we ever have any hope of exploring or contacting anyone. We'll never contact anyone, even in the Andromeda Galaxy. But the Milky Way, if there's someone there, we could at least aspire to contact them. So it's worth that effort to listen. We don't spend much money on it. We spend too little on it, I think. It would be a tremendous discovery if we made it.
If
so
we
it's
found
worth
something like us.
It's worth listening because, and when SETI started, back with Frank Drake and Carl Sagan and others back in the 60s, no planets had been discovered beyond the solar system. None. The only planets we knew were our planets. Now, as I said, we've discovered thousands of planets, confirmed discoveries, and the statistics tell you there are billions of them out there. So virtually every star probably has a planetary system. But as I say, you've also got to have the time to make things like us, and that's a tortuous process. There's no inevitability to evolution. I think it's not to be seen as some march to complexity. Evolution, it does what it does. It's single-celled organisms were very, very good at just surviving and getting on with it for most of the history of life on Earth. So it may be that complex multicellular life is kind of just an aberration, really. It's just a bit of a lucky accident. We only discovered that the structure of atoms in the 20th century.
Or that atoms existed.
Well, yeah, it was up for debate. The turn of the 20th century, one of the debates in science, is there such a thing as an atom?
Yeah.
It's incredible. And Einstein did it in 1905. One of his famous papers was on Brownian motion, which one of the three famous papers in that year. The other one was special relativity, and the other one, when he got the Nobel Prize for, was the photoelectric effect. So the third one. And
Einstein, we should just retroactively give him like a dozen Nobel Prizes.
It's astonishing.
Yeah,
He didn't get the Nobel Prize for relativity. He got it for basically the foundations of quantum mechanics.
Yeah.
We discover that matter's made of atoms. And then we very quickly discover after that the atom is electrons. Initially, we have this almost solar system-like model that it's a nucleus, a dense nucleus with an electron going around it. And then we discover the nucleus is made of protons and neutrons. That's 1930s, by the way.
That orbit model is still the symbol for an atom.
Yeah. The atomic
we kept it
energies,
just because it's classic, but atoms look nothing like that.
No.
Right.
And so then quantum mechanics comes in, tells you can't have that because charged particles moving around in the vicinity of other charged particles radiate energy away and wouldn't be stable. And that was known. And so then you find that the nucleus is made of protons and neutrons. And as I said, the neutron, it's a 1930s discovery. So we're not that long ago.
As Jupiter is made of gas, could you fly a rocket straight through?
No. So you could fly a rocket through the upper bits of its atmosphere, where it's not quite as dense. But if you go down towards the core of Jupiter, the pressure becomes so high and the temperatures become very high. We think there are all sorts of exotic materials. We don't really know what's at the center of Jupiter. We have a spacecraft called Juno at the moment, which is orbiting around Jupiter to answer that very question, trying to work out what is actually in the middle. We think that exotic things called metallic liquid hydrogen and all sorts of really strange materials. But if you tried to fly a rocket through the center, it wouldn't get very far. It'd get squashed and crushed and melted. And then it may well hit something very solid indeed in the core.
And is there actually any proof for the multiverse theory?
So first of all, there's no proof. And secondly, there are lots of different versions. One of the ones that's interesting to physicists is something called the inflationary multiverse. So what is that? Well, the idea is our best theory of, let's say, the way that the galaxies are distributed in the sky. So we can map that. So it's something we can observe. We can look at where the galaxies are. Then we have a big map. It's called the Sloan Digital Sky Survey of where the galaxies are. And when you look at them, then they're random in a sense, but there's also some pattern to it. And in particular, they tend to, roughly speaking, lie on circles in the sky. So they're not completely randomly distributed. We can trace that all the way back to patterns that we see in the oldest light in the universe, which is the light that, if we look as far as we can out into space, then we're looking back in time. You might be ready to participate in the record event, to go at the Stargazing World Record, to go and look out at the night sky and get the most people ever looking out into the night sky at the same time. You could also likely, I think, see the Andromeda Galaxy. Not quite sure about the time when it's going to be up, but look at the Andromeda Galaxy. You'll see light coming from it, which has travelled for 2 million years. So you're looking back in time, 2 million years, because you're seeing the Andromeda Galaxy as it was 2 million years ago. Now, many physicists think that inflation doesn't all stop at once, but stops in little patches. And so you have a little patch of this rapidly expanding universe that slows down and makes a big bang, and that would be our universe. And then the rest of it carries on, another little patch slows down and stops, and you get another big bang, and that would be a different universe. Another bit stops, and you get a big bang and a different universe, and so on. So that's called the inflationary multiverse, which is what was in your question, a multiverse, a load of bubble universes, if you like, essentially an infinite number. And that could be our reality. It really could be that our entire universe, which is much bigger than the universe we can see, with 2 trillion galaxies in it, is one bubble in a multiverse of bubble universes.
Why some planets like Earth and Jupiter have a magnetic field and some planets like Mars and Venus don't.
So Mars is a small planet compared to the Earth. It means that its surface area is larger in relation to its volume. You see this in the natural world, actually, in animals. So things like little mice and little bats have to work a lot harder to keep their body temperature. So all planets, when they form, you've got loads of rocks coalescing together. You get heat in the center. That's added to by radioactive decay in the center of the planets. So you've got a certain amount of heat in the core, and it's been radiated off into space. And the smaller the planet, the faster it radiates the heat through its surface, because its surface is bigger in relation to its volume. So you would expect a planet like Mars for its core to solidify. You've not got this nice iron core that can spin around anymore, molten iron core, and so you lose the magnetic field.
The fact that we observed that the universe is accelerating in its expansion.
And Nobel Prize has been given for the observation,
Brian
not for the
Schmidt.
understanding. Yes.
Yeah. There's this remarkable idea, which is in Einstein's theory, this idea that you can have a kind of energy in the universe, let's say, or a thing, whatever it is, because we don't know what it is, but something that makes the universe, that space stretches, increase. It's one of the great mysteries. I think it's the smallest number in all of physics. 10 to the power minus 122 or something in appropriate units, right? Which is an absolutely ridiculously. So it's a tiny, 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 tiny thing that's causing this rate of expansion, but it's not zero. Because if it were even slightly bigger, we wouldn't be here. So the universe would have been blown apart. So it seems very unusual. I saw the other week, or the other day actually, that there's some research that's linking that in the framework of a string theory or M theory to dark matter. So there's a kind of an idea that if you fix that, you get a prediction out that there should be dark matter, but it turns out it's to do with extra dimensions and gravitons in extra dimensions and things. So it's quite interesting. So I think there are some very interesting areas of string theory where progress is being made quite remarkable. We have the Higgs particle. Most particle physicists expected there would be other particles discovered. There's a particular
in
theory.
that same experiment.
Yeah, at LHC. So there's a particular theory which motivated by string theory a long time ago called supersymmetry, which is a property of us.
It's been around for many decades.
Yeah, and it came initially from either from string theory or from some other bit incorporated in. I can't remember historically where it came, but it essentially predicts double the number of particles that we see, fundamental particles at this energy. And they would have been great candidates for dark matter, by the way, which is an astrophysical discovery. So we should say, I suppose, the one sentence description of dark matter is that we see the universe, there's far much more matter in the universe than we can see.
The moon was made.
It was made in an impact. So very early on in the life of the solar system, so let's say 4.5 billion years ago or so, we think that a planet about the size of Mars collided with the young Earth. It's sort of a glancing blow, actually, which caused a lot of rubble to go out into space, formed momentarily a ring around the Earth, somewhat like the rings around Saturn, but then that ring very quickly coalesced into the moon. So we think that the moon is made of mainly bits of the Earth and also bits of this other planet that glanced off it. Something like 4.5 billion years ago. It's very, very early, very soon after the Earth formed.
Where are we with neutrinos now? I thought they're sort of understood. We solved the neutrino problem in the sun. A Nobel Prize was given for that. Is there anything left to discover about this elusive particle that belongs in the I would say tree of life, in the particle tree of life?
Yeah, I mean, there are neutrinos are fascinating things. That they're very, very, very. They're almost massless, but not quite.
And that matters.
That should ring bells. You know, it's like, why? That's the thing about science, isn't it? You go, well, why is this unusually light? Or maybe it isn't. Maybe the other things are unusually heavy. But it's telling us something.
And it's only neutrinos how hard it is to interact with them that gives me any belief at all some other set of particles that exist that we don't interact with. Because neutrinos are our own species.
Well, they interact through the force. So
yes,
they interact
but
through
that's our little world here, right? Any other symmetric particles, there are other forces that mediate them, is that correct?
So if you have extensions to the standard model of particle physics, then you can have forces that change things into other things, and so different forces. But as far as we know, as far as that we have discovered, is by the three forces, the strong nuclear force, the weak nuclear force, electromagnetism, and then hanging out there, as we've discussed, is gravity in really a different framework at the moment.
The Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again. Or some of the other theories, there's a theory called eternal inflation, which is a theory that, and it's actually the most popular theory, I think, at the moment, for what happened, for why the Big Bang is the way that it is. Because it's got some very special features, the Big Bang, which we could talk about. But inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. And there was doubling in size in the most popular of these theories every 10 to the minus 37 seconds, which is 0.00000 with 37 noughts, 1 of a second. So it's an unimaginably fast expansion. And then the idea is that draws to a close, so it quite naturally sort of dies away and the expansion slows down. And all the energy that was taken, that was causing that expansion, sort of gets dumped into space and heats it up and makes particles, and that's what we call the Big Bang. And those theories, the slight extension to those, say that slowing down just happens in little patches. So most of the universe, the overwhelming majority of the universe, is still inflating at that insane sort of speed. And just little patches stop and they're Big Bangs. So you get multiple universes, a multiverse. It's called the inflationary multiverse. And we are in one of those bubbles. And that's one of the more popular theories.
Mars is the only planet we'll colonize beyond Earth, but it's an easy planet to colonize. It's got water in abundance below the surface, we're sure, or frozen in the ice caps. It's got all the minerals that we need to build a civilization. We have the technology to go and extract the water and turn the water into oxygen and hydrogen for us to breathe and to make rocket fuel and electricity, all the things we need to build a civilization. So we know how to do it. So it's just whether we want to or when we want to. Most of the plans I've seen to go to Mars involve setting up the base first with robots and then going to the base. So it's almost we build the base first and then we go and move in. And I think that's what we're going to do.
Do you think we need to terraform?
Terraforming is changing the atmosphere of the planet. And that's a longer term goal, but we know that we could do it in principle. There's a place called Hellas Basin on Mars, which is a big, almost certainly an impact crater, impact basin actually. It's 9 kilometers down to the floor. So that means that although it's so big you couldn't see it, if you put Everest in the middle, you could look down on the summit from the edge. It's so deep that the atmospheric pressure is so high at the floor of the crater that liquid water can occasionally exist at the floor. So already, although Mars's atmosphere is very thin, there are places that are so low in altitude that the pressure is high enough for liquid to exist momentarily there, even now. So you can see that the atmosphere of Mars doesn't need a lot. It needs things like greenhouse effects, carbon dioxide and things thrown into the atmosphere. But then you can imagine growing plants, and the plants will produce oxygen, and the water's there for them to do that. And so you could imagine at some point in the future that we end up with an atmosphere on Mars again, because it did have one once.
Do you think?
I'm a few years your senior. I don't know if you would remember this, but I definitely do. The era where no one was thinking or caring about moons.
Yeah.
In the solar system.
Yeah.
You know, we have a dead moon orbiting us, oddly large, but fine. Let's go look at the planets.
Yeah.
And so every mission out to the planets, they looked over their shoulder and found moons which had way more geologic diversity than anything we're finding on the planet.
I found it interesting because
when you were in school, where were we
pre-Voyager? Well, Voyager. So
see, I'm pre-Voyager, and Voyager turned the moons into worlds.
Yeah,
that's what happened.
Yeah. So the idea you have a habitable zone in a solar system, which is the zone within which, if you have a rocky planet orbiting and everything's right, and the atmosphere is right, you could have the conditions to support life on the surface.
Well,
so liquid water on the
water.
surface, let's say.
Right.
And so.
But that turned out to be needlessly limiting.
Well, exactly. So you just say, well, Mars, Earth, Venus in our solar system.
That's it.
But then you find the habitable zones around gas giants. That, as you said, that was the great discovery of Voyager, I would say.
Yeah, it began with Voyager, really, for sure.
Yeah. Which should be early 1980s. Right?
Do you think that one day we will use wormholes to time travel?
It's one of the big questions in theoretical physics, whether those things, first of all, can exist. They can, given Einstein's theory, but there's a question about whether they would be stable. So there's a question about whether, if you tried to send information through them, then they would collapse. And it's a big debate at the moment, actually. You use it as a time machine to go into the past. And I think most physicists think not. They think that whilst they could exist, they would be unstable and collapse again. And so you'd never be able to send information through, let alone a person. Even one little light signal wouldn't get through it into the past. But we need the more advanced theory, the quantum theory of gravity, to be sure.
The galaxy is 100,000 light years across. There are 200 billion star systems in it. It's big.
It's too big.
But that's not... So you could just about perhaps conceive in the far future of beginning to spread out into the Milky Way. You could conceive of that, given hundreds of thousands of years, right? But then you go, well, where's the next galaxy? Andromeda. Right. It's over 2 million light years away. So the idea that you would get across a distance of 2 million light years with any conceivable technology is, to me, probably... it takes a light beam to 2 million years. So if you want to talk to someone in Andromeda, it will take 2 million years to get a message out there and 2 million years to get it back. So there's a 4 million round trip. That's the nearest galaxy. So it's big, right? Space, that's the thing. But so you can imagine possibly the Milky Way. It's some chance if there are other civilizations there talking to them. But I think beyond that, I just cannot conceive of how it would be done.
Is this relative, though, in perspective to the single-celled organisms that existed billions of years ago in comparison to us? Do we really think that we're the end-all, be-all, and this is the last stop on the road to evolution? No. Isn't it possible that we get so advanced, if we live to be another billion years, that we can, all these ideas that we have in our head about the laws of space and time and what particle physicists are trying to figure out and what string theorists are prescribing as far as 15 different dimensions? Is that what you said? That
they change their mind all the time. That's pretty unfair to them. But
well, I want to get into that because I don't understand string theory.
No, I don't know.
But I don't understand what you're saying either.
Well, no, you're right.
But my idea is that if we continue to go on the same path, isn't it possible that we will achieve some unfathomable level of technological proficiency or of control over matter or of an understanding of the universe at such a deep level that we can violate all these things that we now consider laws, like the laws of...
Yeah, so the laws would have to be approximations to some deeper laws.
There was some recent announcement, the biggest jet from a blackbird discovered ever.
Yeah, not long ago, we didn't really have any observation of how things behave in the vicinity of black holes. And so I would put it in that box. We've got several observations now. We've got the radio telescope observations from the Event Horizon collaboration that have shown us how the magnetic fields work, for example, around the black hole in the Milky Way. We've got these jets, which are giving you access to the magnetic structure, presumably in the way that they spin.
Thank you for putting it in that context. Now I can understand. It broadens the astrophysical data set on which we can sharpen our hypotheses for what's going on.
Yeah, because they're hard things to observe.
Yeah.
And of course, you can't observe the interior because it's inside this thing, Event Horizon. But what you can do, and we are doing, is observe the way that material behaves in the vicinity of them. Or the other remarkable thing we've been able to do in the last few years is watch them collide and see how the ripples in the fabric of the universe come out, and we can detect those ripples. So all these things are allowing us to probe these objects and it's worth remembering that they were non-spinning ones were described by the work that Karl Schwarzschild did in 1960. So months after Einstein had published the theory of general relativity. He didn't know it at the time, but the mathematical description he found, which describes how space and time are distorted in the presence of a star, a non-spinning star, is kind of important. Those fully describe a black hole that isn't spinning.
So we've got, more than a century of mathematical foundation for this. Yeah.
And then you go forward to 60s.
With no data. No data.
No, and then so it takes another 50 years, by the way, for someone to work out what it looks like for a spinning one, which is Roy Kerr. It's a famous Kerr solution. But those two solutions are there. They're in Einstein's theory in a sense, and they describe the black hole. But observing them is something that we haven't been able to do till recently. So
and multi-wavelengths as well.
So now we have radio observations, the gravitational wave observations.
I'll be a little kinder to that.
I'd like to know how you distinguish and identify the different kinds of things out in the cosmos that have an impact.
There are many independent measurements that build to our particular worldview at some time. So, for example, when you talk about the age of things, the age of the Earth, the accurate measurements come from, one thing is they come from radioactive dating, which is a very high precision technique to date rocks. And we can date the oldest rocks on the Earth, and we can date the oldest meteorites, and we can do those things. And we always get, for the oldest things, around 4 billion years or so, and you can hone it in from there. Then you can look at the sun, and you can say, well, we can do something called helioseismology, which is really like looking at solar earthquakes, if you like, solar quakes, and looking at the way the sun oscillates and rings. And you can use that to measure the amount of helium as a cross section through the sun. So we know that the sun shines by making hydrogen into helium in its core, which would suggest that there should be more helium in its core. And we know how bright the sun is, we know how much energy comes out, so we know the rate of nuclear reactions that we need to produce that amount of energy. So we can look and see how much helium's there, and that tells us how old the sun is. And you get the answer, which is about 4.7 billion years or so. So from a completely different measurement, you get a measurement that's consistent with the age of the Earth. So you build up this picture, in this sense, cosmology, from many different measurements, and they all appear consistent. So then you judge, if you make a measurement that jars with that whole lot, then it gives you a sense of that makes you perhaps suspicious. If it contradicts the whole swathe of other experiments, let's say we found out, well, actually, I'll give you a very good example. Which is that in the 1990s, we had a measurement of the age of the universe, which at the time, based on the expansion rate we'd measured, was about 11.5 billion years. And we had a measurement of the age of systems called globular clusters, which are old star clusters in the Milky Way galaxy. And the age of those was about 12 billion years. So the age of the universe was measured to be younger than the oldest objects in the universe. And that was the case in the 1990s. So what did people do? They just carried on measuring things. And then in 1998, a physicist who's now at ANU in Canberra in Australia, Brian Schmidt, and another team in America were looking at supernova explosions in the distant universe and found out that they were dimmer than expected. And it turned out the interpretation was that the universe is accelerating in its expansion. A complete shock. It's like we thought the universe was slowing down. It turned it was speeding up. And that changed our measurement of the age to 13.8 billion years. But there was a time when there was a big inconsistency between the age of the universe and the oldest things in the universe, which were older than the universe. So you take data seriously and you hold it, and you're allowed to have a contradictory position. You don't need to make a judgment. You say, well, there's something wrong, but we'll carry on measuring. And what you find almost always, our worldview is quite sophisticated now, and the key thing is consistent.
Nice. So inflationary cosmology theories say that before the universe was hot and dense, which we tend to call the Big Bang. Before that, the universe was still there, and it was doing something else, which was an exponential expansion. So it was expanding exponentially fast, way faster than the speed of light. Then it stops, and all the energy that was causing that expansion gets dumped into space, heats it up, and that's what we see, the particles and energy today. So those theories are kind of interesting. But they also suggest that there are theories called eternal inflation theories that say, well, how long did that period of expansion go on for? And does it all stop at once, or does it stop in patches? And if it stops in patches, if it stops in a little patch, you'd get a big bang and a universe. And it stops in another patch, you get another big bang, another universe. So these theories suggest perhaps there are an infinite number, possibly, of big bangs, in inverted commas, which would mean there are an infinite number of universes like ours. And they're being created now, all the time, and they will continue to be created forever. So you get this fractal multiverse, ever growing exponentially fast. And really bizarrely, those theories have some support from the cosmic microwave background. They're theories that explain the structures we see. I should just underline the fact that this is speculative in a sense, but it's relatively mainstream. What one of my colleagues noticed, and some physicists have noticed, is if you were some kind of omnipotent deity programmer and you wanted to run what's called a Monte Carlo simulation to say, well, I'll vary the strength of gravity in one universe and vary the mass of the electron in another one and vary these physical constants, see what happens, then this is probably the kind of thing you'd do. This is what it would kind of look like. So that you can make an argument that the universe, in some sense, looks like one of these kind of so-called Monte Carlo simulations, because it gives you the possibility of generating every possible number of different ratios of the strengths of the forces of nature and all these things. So I just have to emphasize, this is way out there on the edge, but it's fun. And what is fun and interesting, though, is that the wind all the way back, the inflationary cosmology bit is probably the most widely accepted theory at the moment for how the universe got to be the way it is. And it does lend itself to this idea that there may be a multiverse. And it may be that in each different pocket universe, if you like, you can have different physical constants. So most of them wouldn't allow life to exist, but some of them would. So our universe looks very fine-tuned if you look at it, in a sense. It looks like the laws of nature were very slightly different. You wouldn't get carbon, for example, produced in stars in large quantities, which you need in order to, and when the stars die, the carbon and the oxygen come out and they relapse into another generation of stars and solar systems, and that's how you get the heavy elements that make up our bodies. And so all those things you either try and find an explanation for why the laws of nature are the way they are, or you go to one of these multiverse theories and say, well, actually, every possibility occurs in nature. And then we shouldn't be surprised that we live in a universe that seems fine-tuned for life, seems perfect for us to exist in, because every possible combination of the laws of nature exists somewhere. And this is where cosmology is at the moment. This is genuine. You could go onto the web and Google, you'll find a 1,000 review papers on what's called inflationary cosmology. And it is cool and interesting, actually. Infinite numbers of infinite universes. These theories exist. So the question
we can look so far out into space that we can see the light from just after the Big Bang, about 380,000 years after the Big Bang, actually. And in that light, before there were stars and galaxies, there are also patterns that match on to the way the galaxies are distributed in the sky today. And where did those patterns come from? Well, the best theory we have is a theory called inflation, which says that before Big Bang, in the sense that before the universe was very hot and very dense, it was still there and it was kind of cold and empty, but expanding very fast. And then that very fast stretch of the universe came to an end, slowed down, and in the slowing down, the universe got heated up and all the particles out of which the stars and galaxies are made were created. So that's called inflation. There's good evidence for that.
And no time.
Mars is the only planet.
We could go arbitrarily far into the future by flying around in a rocket very close to the speed of light. So we could come back a million years in the future and look at the Earth and find out what had happened. You can't go back as far as we can tell. A way to think about the characteristics of black holes, the physics inside black holes, is not understood. We don't know. Our theories don't work. We need what's called a quantum theory of gravity to make progress there. So that's the unification of quantum theory and relativity and general relativity, which is what string theory is an attempt to do, but we don't know whether that's the right theory. So this is the edge of knowledge. So we don't know. So we don't know we don't know how to describe black holes properly. We don't
So
have a theory that's capable of describing it. We can describe the edge, so this thing about an event horizon and all that stuff, that works. That's not a problem in Einstein's theory. So the idea that if you have a sufficiently dense object, then there's a region around it out of which light can't escape, because space and time are too curved for light to get out. That's fine. The theory describes that properly. But when you start asking questions about what happens at the center of a black hole, the singularity, the very idea it's called a singularity tells you there are infinities in the theory. The theory is doing things. It's infinitely dense. It's infinitely small. Well, no, it won't be. We don't have infinities in general in nature, other than perhaps the size of the universe, as you say. But so there's something going on there, but we don't have the physical theory. We don't have the tools to describe it. It's an active area of research. So I don't know is a good answer in science, right? And so speculation's fun, but ultimately, we're talking about a regime of nature, which our current theories are not capable of describing with any authority. And that's the inside of a black hole.
Graviton, I mean, is that a real particle?
I think most physicists would say that quantum mechanics is base theory. The reason I'm careful is there are some people who would say general relativity is a space-time is a real thing and all that. But generally, most people would say quantum mechanics is underlying it. And that if you have an interaction...
In other words, quantum physics is foundational to the universe in ways that even general relativity would not be.
Yeah, so we could talk about this later, but the idea that space and time, or space-time, emerge from a quantum theory is very fashionable at the moment, partly because of the study of black holes. So how would we picture the electromagnetic force in particle physics? So we know that if you put like charges together, they repel and so on. So what's happening there? Or if you bring magnets together, right, they repel each other. Everybody knows if the North Pole together and they repel. So what's happening? In particle physics terms, you picture that as the exchange of a photon. It's a particle of light that goes from one particle to the other and essentially carries the force. So that's what our particle would picture that force. All forces. Although it is true to say that because gravity is so weak, so this is the other thing to say, it's tremendously weak compared to the other three forces of nature, of which electromagnetism is
Here's
one.
what I tell people, you've surely done this in class. They say, well, how weak is gravity? Well, I can pick something up off the floor against the wishes of Earth.
Exactly, yeah.
Yeah, the whole Earth is pulling on this ball, and I can just pick it up off and kick it
And
into
you're
the goal.
using electromagnetism. That's what's happening. So your muscles and all that thing. So this is all electromagnetic force, which completely destroys, as you said, the gravitational force.
Right.
But gravity is only additive. So it only adds up in the universe. So it is the dominant force on cosmic distance scales. That's the point about gravity.
Okay, so gravity's weak. That somehow bails you out of this problem?
Well, it just means that we don't have experimental access to them.
Okay.
Because it's so weak.
Whereas we do have experimental access to photons.
Yeah. Unless you could potentially have access if there were extra dimensions in the universe that are configured in the right way.
Physicists are always throwing in extra dimensions.
Well,
whenever you need it,
It is interesting, though, that string theory works in tensions and only 10 dimensions mathematically. So, observation, right? So,
I mean, I don't have the background to string theory.
I think it depends what you mean by string theory. I mean, if you go back, a few decades, you talk to Brian Greene, for example, and when he started working in this area, great book, The Elegant Use, is a beautiful description of string. And so I think the idea initially with the hope was that you'd have a theory and you could write it down. It's a theory of everything, and it would predict the universe as we see it.
And then you go home and you're done.
And I think that's gone as an idea. But the basic idea of these, I mean, why is it called string theory? It's because particles are not point-like. These strings are like little string loops. And that idea, I think, is the foundation of most modern theoretical theory. But it's got more complicated, much harder. I think the initial idea that you could just predict everything from one number maybe has gone away.
One simple equation on one line.
But there is tremendous progress being made in string theory. So it's not gone away. It's just become more complicated, I would say. So the question then becomes, well, how likely is it for simple life, if it arises, to make its way into a civilization? And that's where the biologists come and kind of calm the astronomers down and say, well, you might think there are lots of places for life, we would agree. But on Earth, it took 3.8 billion years to go from the origin of life to a civilization, which is about a third of the age of the universe, give or take. So you had to have an unbroken, stable line of life that evolves in the right way, as it were. First of all, it gets complex. I mean, there's a thing called the Cambrian explosion in the history of life on Earth, which was about 550 million years ago or so, which sounds like a long time. But for 3 billion years before that, there was nothing that we would call complex. Single-celled organisms doing some clever stuff like photosynthesis, but not much. And then suddenly you get a big jump in the oxygen content of the atmosphere on Earth, which was to do with photosynthesis and some geology in play with it. That's how the oxygen gets into the atmosphere. And then you get a big jump and you get complex life emerging. And then pretty quickly, 500 million years or so, you go from complex things to a civilization. But even then, you think about Homo sapiens we mentioned earlier, they only arose 200,000 years ago. So for the vast majority of the history of life on Earth, there's been nothing that could do anything clever in the sense of thinking and building spacecraft and radio telescopes. So there's a legitimate debate about whether the undoubted increase we know now that there are homes for life out there in the Milky Way. They're very common, and we know that. But what we don't know is the probability that life will emerge in the first place, and secondly, the probability that will be turned into a civilization. And I think that's very low. So I think the probability, if I guessed, I would say the probability that life will emerge given the right conditions is very high. And what one piece of evidence you could put forward to that is that it did appear to emerge on Earth as soon as it could after the formation of the Earth and the oceans. So you get life, but then it took a long time on Earth. So you might say, well, the probability of it doing anything intelligent, interesting are quite low, maybe less than 1 in 20 billion. In which case we end up being the only civilization in the Milky Way at the moment. If it's possible, you can make that argument. And my experience is academic biology.
Oh, wow.
And so that seems to be, it's one of the best theories for the evolution of our solar system. So what are the chances? The chances of that are so minuscule, like tiny. So that's the thing I think about these rocky planets. In order to get a civilization on them, I think you need quite unusual solar systems. And that would be a guess. And you need quite unusual stability on the planet for billions of years. And that's why I think we might be quite lucky. What we strongly suspect, and I would say no, is that in that process of going from order to disorder, complexity emerges naturally for a brief period of time. So it's a natural part of the evolution of the universe that you get a period in time when there's complexity in the universe. So stars and planets and galaxies and life and civilizations. But they exist because the universe is decaying, not in spite of the fact the universe is decaying. So our existence in that sort of picture is necessarily finite and necessarily time limited. And it is a remarkable thing that complexity has got so far that there are things in the universe that can think and feel and explore it. What do you mean? There's very little evidence for it at the time back in the 60s. But over the years, the theory called the Standard Model of particle physics passed all experimental tests. So we got to the point where we thought, right, okay, we will build a machine that will either disprove or prove that theory. And the LHC is such a machine. If that theory is correct, which it now seems to be, the prediction is you must find the Higgs particle at the LHC or some kind of Higgs particle. And indeed, we found it.
Since the universe contains billions of stars, why is the night sky dark?
The people thought about it for centuries, and it's called Olbers' paradox. A Dutch astronomer, was Dutch, wasn't he, Olbers?
I think so, yeah.
He thought about this, and he came to the conclusion that if the universe had been around forever and it was infinite in extent, then you could look up and every line of sight would end on a star. And if there'd been enough time, then the light would have traveled time to come to us. And because every line of sight would end on a star, you would see the sky ablaze with light. And it isn't. And that was enough for Olbers, I think, to say that the universe wasn't infinite in extent. So the answer is that we live in an expanding universe that's 13.8 billion years old,
And that's ultimately why the sky isn't absolutely ablaze with light.
How can light be both a particle and a wave?
Experimentally, we find that when they interact in particle physics, what do we see? We see essentially a game of billiards, right? We see things with mass, or indeed with no mass, in the case of photons, little particles bouncing off each other. In order to describe where they're going to go. So you can ask the question, I've got a particle here, where's it going to be at some later time? Where's it going to go? Mathematics that describes where it's going to go is very wave-like. And so particles behave like waves in the sense that if you want to calculate where they're going to go, you end up with things you get with waves, properties of waves. So the way they move is not like the sort of particles we can imagine. If you bang these two together, you go boing, and that one goes off. You can calculate it, but the maths you use is quite wave-like. So for example, with a wave, you can get what's called interference, which means that the peak of one wave lines up with the trough of the other one, and the waves cancel out. And you get that with the way that particles move around. The best thing to say, my prejudice that particles are particles, but the way they move is not like the sort of particles we can imagine. If you bang these two together, you go boing, and that one goes off, and you can calculate it all, but the maths you use is quite wavy and wave-like. So that's the way I look at it.
Do you think time travel will ever be possible?
Not into the past. If you travel at 99.9999999, that's 8 nines % the speed of light, to Andromeda, which is 2.5 million light years away, and then turn around and come back again, then for you on the rocket, 100 years will have passed on the round trip journey, but 5 million years will have passed on Earth. So by travelling fast relative to people who are stationary, the clock runs slow relative to theirs. So you can travel into the future, arbitrarily far into someone else's future. But into the past, it's true to say, you know, that Einstein's theory of general relativity, his theory of gravity, allowed you to curve space and time. What I'm talking about there with travelling to Andromeda back is what's called special relativity. So it's flat space and time, and that you definitely cannot go into the past in special relativity if space is flat. If you're allowed to curve space-time, then there are solutions to Einstein's general theory of relativity that allow you to build wormholes, which would allow you in principle to take shortcuts around. So although you can't exceed the speed of light on the surface, it's like going to Australia but going through the Earth rather than going around the edge. I believe most physicists who work on quantum gravity think that there won't be stable wormholes in a quantum theory of gravity, but that's not proved as far as I know.
Because you don't have a proper quantum gravity theory.
Yeah, the thing travelling to the past doesn't seem to be the right way to build a universe, and indeed, in general, the universe seems to be built such that you can't do that. Interestingly, though, when I said about the electron that can be anywhere in the universe, it's not only anywhere spatially, it's temporally as well. So in what you do in Feynman's path integral approach is integrate over space-time. So you allow it to do all paths, including paths in the past. Right, that's what the way it works, but they all cancel out. But that seems to be a calculational thing. I tend to restrict myself to the galaxy. Right. So I do think it's possible that at the moment there's one civilization in the Milky Way. And I think that's important, actually. And it goes back to what I was saying at the start about the astronomy and cosmology being part of the framework within which you have to think. If you're looking for meaning, or you're looking for how we should behave even politically, that has a bearing to me. I mean, imagine that we're the only place where there is intelligence in this galaxy. And how should we behave? Right. Should we actually, notwithstanding the fact that we're tiny and fragile things and insignificant physically, should we consider ourselves extremely valuable? There's a theory called the grand tack theory, which is, so it's very hard to explain the evolution of our solar system. So when you do computer models of solar systems, you don't tend to get 4 rocky planets too close to the sun and 4 big gas giants further out. I say this because it shows you how lucky we might be. They tend to form these big gas giants and migrate inwards towards the star. So in almost all the computer simulations, just because you've got this big gas giant orbiting in all the dust around the star, they tend to drop inwards. And it looks like Jupiter did that. So it looks like it formed and came in almost to where Mars orbits today. And cleared out the region around Mars, actually, which is maybe the reason Mars is so small compared to the other, to Venus and Earth. But then Saturn was coming in as well.
Just along
in the galaxy, 20 billion, something like that. So 1 in 10 stars.
So the odds of complex life out of our incredibly fortunate situation, but the odds of that occurring on any of these billions of other planets that exist.
We don't know. But let's say the Earth is, let's say it was on the fortunate side. So we're talking about, give or take, 4 billion years, right? From the origin of life to now. And we have a civilization now. And we've had it, our species has been around, what, 250,000 years or something? So it's just now, basically. So let's say 4 billion is on the fortunate side. Let's say that it was double that or triple that on the average. Suddenly, that's the age of the universe. It's a third of the age of the universe it took. So how many of the worlds have been stable for 3 or 4 billion years? That's quite a tall order, actually. I think there must be, even in the solar system, I would not be surprised if we find microbes on Mars or on some of the moons of Jupiter or Saturn where there's liquid water. And the reason is, if you think about, the reason I think that, and it's a guess, is because if you look at the history of life on Earth, so Earth formed, there was no life, it was a ball of rock. And almost as soon as it cooled down, we see evidence of life. So certainly 3.8 billion years ago, possibly even further back than that, we see evidence of life on Earth. So somewhere along the line, geochemistry, active geochemistry became biochemistry on Earth. And we have some idea, that if you get gradients of temperature and acid and alkaline and the conditions that are naturally present on the surface of oceans, then complex carbon chemistry spontaneously happens. So we know that life, almost certainly we know that life began on Earth. I mean, the other option is it came from space or something like that, but it probably didn't, right? It probably began on Earth. So that means that at least here, that happened. And that we know that the conditions that led to the origin of life on Earth were present on Mars 4 billion years ago. And we know that they're present on Europa today. So I don't see that there's anything special. Life is just chemistry. The idea that geochemistry becomes biochemistry is not fanciful because it happened here. So I think that given the same conditions, it would be surprising to me if the same thing didn't happen, in that life begins. To test that is one of the great frontiers of science now. It's one of the great challenges, which is why another reason we're interested in Mars, because we know those conditions were there. We know there were what's called hydrothermal vent systems on the floors of oceans on Mars 3.8 or 4 billion years ago. So it would be good to know if what I've said is right. And the way we find out is to find life or evidence of past life. Einstein's theory essentially predicts its own downfall. It says that, say, at the center of a black hole, let's say in a collapsing star, that there's no cutoff. It drives you in that sort of gravitational collapse to a point of infinite density, infinite space-time curvature. So it's a so-called singularity. But there are very good reasons to believe that that's not right. One of them is that we strongly expect black holes to be temporary structures. So they return their energy to the universe again, almost certainly, and this is through the process known as Hawking radiation, which is a first step, one of Stephen Hawking's great contributions. It's a first step towards bringing quantum mechanics and gravity together. And it has with an audience like this, it has the benefit of being quite easy to explain what's happening, actually. So I can do it if you want, which is that, so Hawking realized that quantum mechanics tells you that the empty space is never empty. So in particular, you can picture particles and antiparticles pop in and out of existence all the time. And so they pop into existence, they can borrow energy from the vacuum, if you like, for a certain amount of time before they return it to the vacuum again. And actually, the more energy they borrow, the less time they're allowed to borrow it for. That's called the energy-time uncertainty principle. So it's a fundamental part of quantum theory. So when you imagine on the so-called event horizon of a black hole, you get these particles popping in and out of existence. Just let me say, by the way, that these effects are measurable, and it's one of Feynman's contributions, one of the things he got his Nobel Prize for, showing how that in the light from hydrogen atoms, those little fluctuations have an effect, and you can take them into account. So we know they're there. So imagine on the event horizon of a black hole that the particles pop into existence, and they're going to come back together again. But one of them they end up on opposite sides of the event horizon. That means that they're what we call causally disconnected from each other. They can't come back. You've got one that's inside the black hole, if you like, can't get out. So what happens? Well, the particle that's outside is made real. It essentially radiates away, and it gets its energy from the black hole, ultimately. So the black hole radiates, it has a temperature, it shrinks, because it's radiating energy away, and ultimately it returns its energy back to the universe again. So you sort of know that there's no end of time there. There's nothing really wrong in the center of a black hole. It's just that the theory doesn't work, and it must be that quantum effects and these things, that something must stop you having these infinities and infinitely curved space, and that's the challenge. So we know there's a better theory. The theory predicts its own downfall. Same at the Big Bang, by the way. But we don't know what the theory is. We've not been clever enough to put it together. But the first steps are being made with things like Hawking radiation. Last week, the Europa Clipper spacecraft was launched.
Yes.
On the way to Europa.
We have an entire show devoted just to that. We visited the Jet Propulsion Labs and felt the excitement of everyone there.
It's great, isn't it? It's the first spacecraft I've seen, major spacecraft being built. So I saw the Clipper. And the thing is, the scale of that thing, it's the largest spacecraft, isn't it, that's ever been sent into the outer solar system.
If you add it may be, but there's another important fact. Solar panels have gotten more efficient. In the day, back if you were going to explore beyond the asteroid belt, you couldn't use solar panels because the intensity of the sun wasn't high enough. This one has a very deployable, large solar panel that'll help it along without having to rely entirely on the nuclear decay of plutonium.
Yeah, so it's a huge spacecraft.
Yes.
And the point is that Europa is a candidate for a habitat. In what we know, the people who I know who work on the mission say we know, we're almost sure there's a saltwater ocean below the surface. I think it's pretty indisputable now, so we're pretty sure it's there.
Yeah, but whatever is the skepticism, what would it be were it not a global ocean?
Yeah, it's very difficult to be because, and that's from many measurements.
Was it made of ammonia? I mean, there's not, water molecule is not rare.
Yeah. So it looks like salt water. Almost.
Yeah, and we have a lot of comparative planetology with, is it the Arctic, when it freezes over, you have these chunks of ice that will break and refreeze and readjust, and you can compare the images, and you'd think you were at the frozen Arctic.
Yeah. So and there's more water in the ocean than all the oceans of the Earth combined.
Right.
Geologically active. There are questions about how the ice cracks and moves on the surface. So it's a fascinating mission. So that's Europa. Mars, of course, Enceladus is another one. Saturn's moon. Even out to Pluto. I mean, even
Enceladus is the ones we see the plumes. Geysers, I guess.
Yeah.
When at the right sun angle, you can see who took those pictures. That must have been Cassini. Right.
Yeah.
So
and also there's something from Cassini, the particles in those jets of water, which are consistent with hydrothermal vent activity on the floors. And hydrothermal vents are one of the plausible candidates for the origin of life on Earth. Yeah. So you seem to have everything. The one thing I think Europa's got that arguably nowhere else has is it looks like that ocean has been there for many billions of years. That's the baseline scenario.
And we evolved life in less time than that here on Earth.
Yeah. I mean, it was present, 3.8 billion years ago?
3.8-ish, yeah.
And the Earth's 4.5 billion years old. So,
right.
Yeah, so it looks like you have a habitat that's been stable there. And I think that you can't claim that with anyone else.
It was taught that it took about 500 million years on Earth to get life going. But we were able to revise that number down. Because in the early Earth, these periods of heavy bombardment, it's not fair to start the clock while we're still getting slammed by, still accreting leftover rocks from the solar system as the temperature of the surface of the Earth is high enough to prevent complex molecules. Give us a chance, please. So the periods of bombardment subside, Earth's surface cools, now start the clock. And then it's about 100 million years.
Yeah. So
that's like that.
Which is one of the reasons I think if you speak to many biologists, they would say that might suggest that given the right conditions, then whatever the origin of life is, there's a reasonable probability given the right conditions because it happened quickly here.
Right.
So, but that's not that's not definitive in any sense.
But it's certainly tempting to go there.
But what I find very interesting then is, though, when you ask, okay, but when did life get more complex than a single cell? You're then, I don't think there's any evidence in the fossil record back beyond about 600 million years ago.
It took a while. We languished as single-celled creatures.
3 billion years
Yeah.
plus, but it seems.
So I think people who think about this problem are honest about that. And so in the search for life on other planets, we're really looking for single-celled organisms.
It would be remarkable to see anything more complex.
Yeah.
Well, it would be remarkable to see a single cell, especially if it were biologically different. So you can really show that it's got a different origin. Because it's worth saying that on Mars, the material is exchanged between Earth and Mars. So it's not obvious.
For a time, it is one of the more widely accepted theories about hominin evolution, as they call it, is that climate change played a key role. And actually, there's in my latest series, Human Universe, we focused on a theory which links the climate change, particularly in the Rift Valley, because we know that the big jumps in brain size all occurred in the Rift Valley of Africa. And it's quite remarkable, actually. And that's broadly speaking accepted, I think. Although there's a lot of argument with anthropologists because the data is sparse, But it's broadly accepted there. And it seems that the big jumps in brain size occurred at times when the Earth's orbit was most elliptical. So the Earth's orbit oscillates. It becomes more elliptical and more circular, and there are many different oscillations driven by gravitational interaction with the planets, like Jupiter in particular. And it seems like when the Earth's orbit's most elliptical, the rate of climate change in the Rift Valley is higher and more extreme. And it seems to be the case that there's relatively strong evidence for the case that when you get these really rapid times of climate change, then you get increases in hominin brain size, therefore increases in intelligence. There's a big one 1.8 million years ago, which was a very big increase in the number of species in the Rift Valley, of which Homo erectus was one of them, which eventually led to us, and a big jump in brain size as well. And this was at a time when there's strong evidence for rapid climate change in that region.
So that makes sense, like the adaptability of these animals, experimenting with new food sources, trying out new hunting methods. A lot of them changed from herbivore to omnivore, a lot of the primates that were observed, right?
Well, that's where it gets controversial when you look at the academic research, because sort of Darwinian idea that so you get this pressure from climate change, but then what's the selection effect? Because climate change happens over many generations. It doesn't happen over one generation. So the question is, well, what actually is doing the selecting? What are we selecting for? Why is this group more likely to breed and be more successful if it's more intelligent? So some people say, well, it's because they were forced into groups. So it's group dynamics. It's the fact that you end up with bigger tribes, hundreds of individuals cooperating together. And that's what's been selected for. And you need to be intelligent for that. Some people say, as you said, that it's adaptability. So maybe they have to learn to go fishing, or they have to learn to eat particular different crops, and then maybe that's
right.
So that's a big area of debate about what might have been the selection pressure, this precise selection pressure. But it does seem pretty nailed down that climate change, certainly in that region of Africa, in Ethiopia and Tanzania and through the Rift Valley, had played a role in driving us towards intelligence. And it's interesting that science scale is very small, by the way. I mean, so you go back 4 million years, and things like Australopithecus are around, which are basically upright chimpanzees. The brain is not much bigger than a modern-day chimp. But then you go to 200,000 years ago, and that's when Homo sapiens first emerged, just over 200,000 years, which is not very long ago. And it's quite remarkable, actually. Basically, he published it in 1915, and you can predict that that's what one should look like. And then just about, what was that, 4 years ago now, maybe 5 years ago, for the first time in history, we get an image of one, and it looks like the prediction. In science, at the moment, space science, we have this debate a lot, actually, because, of course, space probes like Curiosity that's on Mars at the moment, that's really cheap compared to sending people to Mars. And so quite often the scientists who want to find out about the worlds will say, well, we should spend it on robots. We shouldn't spend it on people. I think crude space exploration is in some ways, I mean, it's clearly true at the moment that humans can do more than robots, so we can explore the place better. It's about living and working off the planet, which I think is quite a persuasive argument, actually. We've already industrialized near-Earth orbits, so it's already a multi-billion-dollar industry, communication satellites and weather satellites, GPS, whatever. We're already up there. And so learning to live and work in space is, I think, a natural extension of our
about civilization. Plus the fact if you talk to Elon or Jeff Bezos, they point out that the amount of resources available just slightly above our heads is vast. And so I remember I talked to Jeff Bezos actually once, and he thinks really simply, and he said, for example, in the asteroid belt, there's enough metal, I think, to build a skyscraper. What is it? Something like 800 stories tall and cover the Earth in it, right? If you want. Now, we don't want to do that. But his point was that the energy from the sun is all up there. The resources are up there. So you could almost imagine trying to zone the Earth residential at some point in the future to protect the planet and do your heavy industry off the planet, for example. And it sounds like science fiction, except that now SpaceX and Blue Origin, those people have got reusable rockets. So suddenly the economics become sensible. I think expansion is good. And I think we will expand. And I think we will expand outwards because there's not much room left on this planet to expand. That's a whole different idea. It's not about gathering scientific information. It's about a frontier and all the benefits that come from operating as a civilization on frontier, which we've sort of lost on the Earth because there is no frontier left. And so I like that idea. It's one of the arguments often used to say there aren't any civilizations out there in the galaxy. It's called the Fermi paradox. Because if you imagine a civilization that's 1 million years ahead of us, they should have written their presence across the sky by now. You should see them. I mean, you'll see us. If we survive 1 million years into the future, actually even a few thousand years into the future, we will be exploring the galaxy. We will have spacecraft that are going to other stars. We will be doing it. So our signature will become visible, I'm sure. If you look at the surface of the moon, for example, it's covered in craters. And that was caused, they all seem to hit about the same time. And it's about 3.8 billion years ago or so. And that's called the late heavy bombardment. So we know that if you look at cratering rates on Mars and on the moon, it all seemed to happen in this, not all, but a big peak around that time. And that seems to be correlated with Neptune moving outwards in the solar system and into Kuiper belt, basically, or towards the Kuiper belt, and causing all sorts of havoc, and everything comes into the inner solar system. So those things happen. But it didn't happen when life was established on the Earth. So you're always getting things that look like new particles, and then they tend to go away again when you get more data. There's statistics fluctuating around. But we did have hints of which look very like new particles in the old data, and we need to take new data to see whether they go away or not. But one of them, it's a famous thing, it's called the diphoton excess, and it was about 750 times the mass of the proton. Now that's very heavy. The Higgs is 120 odd times the mass of the proton also. So a very heavy new particle, it looked like, which was decaying into 2 particles of light. And so you can see that no one knew what this was because there were over 200 theoretical papers published describing 200 different versions of what it might be. So nobody knows. Nobody knows even if it's there. It might go away. But if it stays, one of the suggestions is that it's this hint of extra spatial dimensions in the universe. So that there are ideas which go back to the 1930s called Kaluza-Klein gravitons. And the idea is that you can have extra spatial dimensions that are kind of curled up small so we can't see them. And the analogy that's often given, which is a good one, is imagine a hose pipe at the bottom of your garden, and if you're a long way away from it, it looks like a line, sort of a one-dimensional thing. But if you walk up to it, you can see that it's actually curved up into a second dimension, so it's a 2-dimensional thing, a cylinder. So space can be like that. And one of the signatures is that you get these signatures of heavy particles, kind of towers of them, almost like harmonics on a guitar string. And this looks like one of those, if it's there. So if we're very lucky and we see hints of something like extra dimensions, then you start being able to probe these effects. So gravity, potentially trying to understand gravity by looking at collisions in particle accelerators, and then you're on your way. So if that it's very exciting if it turns out to be true. I just don't know. Many of these things go away. In time are essentially to be treated as dimensions. So you imagine this 4-dimensional sweep of space and time. Now obviously we have freedom of movement in space. We can go anywhere, backwards and forwards and up and down, come back to the same place. But in time, we don't. We can't walk into the past. We can't halt our journey into the future, although we can vary the rate, actually, that we go into the future relative to other people. So there's something different about the time dimension to the space dimensions. And that difference in the geometry comes from a universal speed upon which everyone agrees. So it's a so-called invariant in the theory. And the last thing I'd say is that the speed of light is a red herring. If you know what that is, it's kind of it's a bad name for something, right? That light happens to go at the speed of light because photons are massless. And actually, in the theory, it is massless objects that have to go at that speed, and objects with mass that cannot exceed that speed. And the speed of massless objects is agreed upon by everybody, and that builds the geometry and stops you building time machines that allow you to go into the past, and leads to E equals mc squared, actually, because you have energy equals mass. So you can kind of see energy, mass, we can change mass into energy and vice versa. The sun does it all the time. What's the c squared got to do with it? Why is the speed of light squared the exchange rate between energy and mass? And actually you can kind of start to see when you realize that what that number is something to do with massless things, actually. So it's a coincidence, as far as we know, that light travels at the speed of light. It is sun. If you squashed it down within 3 kilometers of radius, you'd get this be falling through that horizon now in this room, and we wouldn't notice anything, except that we couldn't get out again. And ultimately, in a few hours, in that case, time would end for us. So you go to the end of time. What happens if you go really close to the speed of light? What happens if you go at the speed of light? Well, special relativity, Einstein's theory, is built such that the distance between any two events in the universe along the path of a beam of light between the events is 0. No time at all. That's the way that Einstein's theory is built. So he asked the question when he was younger, famously, what would the universe look like if I travelled alongside a beam of light? And the answer is that you wouldn't perceive any time. For the satellite navigation system, for example, GPS, the clocks on the satellites tick at a different rate to the clocks on the ground. Over 30,000 nanoseconds per day difference. They're in a weaker gravitational field and they're moving and all sorts of things. Light travels 1 foot per nanosecond. So that's 30,000 feet of position measurement if you drift your clock out by 30,000 nanoseconds. So it's a big effect for when you start using time to measure distance, which is what we do. If you're carrying your watch, maybe you fly to Dallas and back, someone else can take a different path, obviously. And so that a different amount of time will pass for them between those two things that happen. It's a tiny amount, unless someone goes close to the speed of light, or someone goes near a black hole where the space-time is all distorted. One of the coolest things I think about Europa is that the habitat, the potential habitat, requires Jupiter, because the heating, it's liquid because of it's orbiting around a big planet. Mm-hmm. But it also seems to it requires the other moons, Io and Ganymede, to keep it in this orbital resonance, which keeps feeding the energy in from the gravitational field.
The family affair,
But it also might need the material from the volcanoes of Io on the surface of Europa, because they might hide what we call the oxidant, right? So life is...
So you're saying that an Io, which is badly stressed...
It's just one big volcano.
It's one big... So it's volcanic substance faster than escape velocity, apparently. And then which lands on Europa. And it goes into pathways that intersect other moons, Europa included. Yeah. And you do this for 1 billion years.
And then the chemistry... and then it gets irradiated.
It helps out the chemistry.
Yeah, so one of the theories that I've spoken to people who are on the Clipper mission said is that that's part of the battery of life, that chemistry. So life, I can't remember who said it, but he said life, someone said it's an electron looking for a place to land. That's what life is. So it's just, in one way you can see life as electrons moving around. But that means you need the chemistry to
Is that all we are? Just electrons looking for a place to land?
Well, that's what a description.
I'd rather be dust in the wind. Whatever all we are.
But I find that wonderful, because then you've got this habitat, which is a system. And as you said, comparative planetology you mentioned earlier, it's also true of Earth, isn't it? You can't understand Earth without understanding the system, the solar system. You need to understand the moon and how it stabilizes the spin axis, and you need to understand, of course, the sun and the way it interacts with Earth and so on.
1 in 10 stars in the Milky Way having a potentially Earth-like planet around it. This is one of my favourite photographs of the Milky Way. It's taken from the European Southern Observatory in Chile. In the southern hemisphere, they're fortunate because they're pointing towards the galactic centre. The top of this arc is the centre of our galaxy, obscuring a supermassive black hole, 4 million times the mass of the Sun. We're looking at a galaxy with 200 billion stars or so. We now know that most of those, the overwhelming majority, have solar systems. The estimate for the number of Earth-like planets in that galaxy, that's rocky planets, the right distance from their star to potentially support oceans on the surface, is of order 20 billion. So we're speaking about, in terms of 1 in 10 stars in the Milky Way having a potentially Earth-like planet around it. Now, we can't, of course, see the structure of a typical galaxy from within. We have to step outside. And when we step outside and start to look at local galaxies, the scale of the challenge of trying to understand the universe, I think, becomes clear.
It's possible, and it's possible if you have extra dimensions in the universe, right? So the thing is that, so we know gravity is a very weak force. It's by far the weakest of the 4 fundamental forces of nature. Billions and billions of times weaker than the other ones, which you can tell because you can pick up, a phone, even though the planet Earth is trying to stop me doing that, and I can just resist the pull of planet Earth. So gravity is very weak. So that gives you a clue that you can say, well, what energy, how far do I have to go back in time, if you like, towards the Big Bang before it's so hot that gravity is as strong as the other forces? The strength of the forces varies, I should say, with energy. So they change. And we've seen this behavior. So 2 of the forces, so-called electromagnetism, which is the most familiar one, electricity, that one, and the weak nuclear force, which is one of the forces that operates in the atomic nucleus, they are the same force. They're manifestations of the same force. And we've seen this experimentally. And in fact, the Higgs boson is part of that process. And so we've seen the energies that they become the same force. So the idea is the other force, the strong nuclear force, if you go to higher energies and temperatures, converges. And then you'd have some things called grand unified theories. And then gravity makes its lethargic way back and unifies with them at something called the Planck energy, which is immensely short timescales after the origin of the universe, if you want to talk. Very, very hot. So way in excess of anything. So if you just want to just create black holes in a lab, then the naive thing is you'd have to go to those energies, and there's nowhere in the universe you'd never do it. You'd have a particle accelerator the side of the observable universe, and it wouldn't be big enough. Wow. But if you allow extra dimensions in space, so you imagine that, so we would live in a 3-dimensional space, and then there's time as well, so we've got 4 dimensions. If you allow there to be 5 or 6 or 13, I think the string theory, they keep changing their mind. What you can do is you can arrange for that energy scale at which gravity becomes important to come up, so the temperatures to drop. So you can arrange in some contrived way to get to the point where you could possibly access gravity, see gravity in action, as it were, in particle accelerators. And in that case, you would produce little black holes, which would then evaporate away very quickly, we think, through a process called Hawking radiation, and they'd be gone. So you can conceive of a way that you could, if given a big of a leap that there are extra dimensions in the universe, and given that they're configured in the right way, that you can imagine that you could do it as a Big Bang, which we could talk about. But inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. There was doubling in size in the most popular of these theories every 10 to the minus 37 seconds, which is 0.00000 with 37 noughts, 1 of a second. So it's an unimaginably fast expansion. And then the idea is that draws to a close, so it quite naturally sort of dies away and the expansion slows down. And all the energy that was taken, that was causing that expansion, sort of gets dumped into space and heats it up and makes particles. And that's what we call the Big Bang. And those theories, the slight extension to those, say that slowing down just happens in little patches. So most of the universe, the overwhelming majority of the universe, is still inflating at that insane sort of speed. And just little patches stop, and they're Big Bangs. So you get multiple universes, a multiverse. It's called the inflationary multiverse. and we are in one of those bubbles. And that's one of the more popular theories. You need to know that the Milky Way galaxy has got 200 billion stars. Most of those stars now we know have planetary systems. We estimate there are something like 20 billion Earth-like planets, or potentially Earth-like planets, in the Milky Way galaxy alone. So if you're asking questions about what is my place in the universe, you need to know those things, first of all. It's a framework within which you can think.
When you get to those numbers, when you're talking about trillions and billions and all those zeros, my brain just goes numb.
No scientist can picture that number. I mean, even the small number, 200 billion, which is the number of stars in one galaxy. And then when you say 2 trillion galaxies, I challenge anyone to be able to picture that. But it is the reality that we've observed.
If 2 black holes are next to each other, what would happen?
They'd orbit around each other in the same way planets orbit around the sun. I mean, the black hole is just a thing that has some mass. Let's say it was a black hole, 3 times the mass of the sun, then it behaves gravitationally exactly like a thing 3 times the mass of the sun. People think that black holes, everything just falls into it. But of course, everything doesn't just fall into things. If you turn the sun into a black hole, the Earth would carry on orbiting around it in exactly the same way that it does now.
Stuff.
Is it? There is no other planet we can go to other than Mars. You can't go to Jupiter or Saturn. You can't go to Mercury or Venus. So if we want to go somewhere and expand our civilization, it has to be Mars. And everything's there that you need. It's interesting, actually, because we know something about the history of Mars now, quite a lot about the history of Mars. And it's certainly clear that there was water, almost certainly oceans, rivers. And that water is almost certainly still there. So there's certainly ice. There may even be pockets of liquid water below the surface somewhere. So couple that with all the minerals and the resources that we know are there, and you have everything you need. So that's the thing about Mars. It's quite nice relative to everywhere else other than the Earth. You can't go to Venus, right? You just melt. It's, 400 and something degrees and 90 atmospheric pressure. It is possible that the universe is eternal. There's a lot of debate about it, actually, because Stephen Hawking and Hartle had a theorem that said that any universe that always expands has a beginning in time. But there are people that try that you can sort of get away. So that's cutting edge cosmology. I don't know what it would mean if it turned out that our measurements suggested that the universe is actually eternal and it's only our bit of it that had a beginning in this Big Bang 13.8 billion years ago, but there was something before that, we think. How long that existed for, we don't know. Did the framework exist forever? Is it logically necessary? Does it need to be laid down? That's cutting edge. So I honestly don't know, is my answer. It's a question that we will perhaps answer very soon. So I think there's a suspicion now that there may be life on Mars, microbes. It looks like the conditions necessary to support life are present on the planet, in particular liquid water below the surface, and some kind of geological activity. It looks very likely those conditions are also present on Saturn's moon Enceladus and Jupiter's moon Europa. So even on Pluto, actually, it looks like there's geological activity, a lot of water ice, which could be liquid below the surface. So the most likely missions are there's a European mission joint with Russia called ExoMars, which is part of it's already gone, an orbiting bit. There's a rover designed to go and look. And so there's within our lifetime, you can imagine a scenario where we find life has emerged spontaneously on another object in the solar system. Also, I should say, the other exciting thing is that we're at the level now where we can not only find planets around distant stars, we've found well over 2,000, but we can also analyse the atmospheres of the planets, and we're right on the edge of being able to do that. We've done it for some big gas giant planets. And we're looking, I think we've seen water vapour in one of the atmospheres, but it's a gas giant, so it'd be like Jupiter, so there won't be life there. But we're getting to the point now where we can start looking at the rocky planets. We're not quite there yet, and analysing the atmospheres, the chemical composition. And if, for example, you see a lot of oxygen, that's a smoking gun for photosynthesis. Oxygen atmospheres are unstable. I don't think there's any geology known that can replenish an oxygen atmosphere to 20% like ours. It's photosynthesis. So you can even imagine the most speculative of all. People say, what if you saw something like CFCs in an atmosphere, which is an industrial fingerprint? But we're there now. Within the next 20 years, we're going to be there where we can start looking into the atmospheres of these rocky planets. So it could be we discover life on a planet beyond the solar system from its chemical signature. I think expansion is good, and I think we will expand, and I think we will expand outwards because there's not much room left on this planet to expand. That's a whole different idea. I mean, it takes a light beam to 2 million years. So if you want to talk to someone in Andromeda, it will take 2 million years to get a message out there and 2 million years to get it back. So there's a 4 million round trip. That's the nearest galaxy. So it's big, right? Space, that's the thing. But so you can imagine possibly the Milky Way. It's some chance if there are other civilizations there talking to them. But I think beyond that, I just cannot conceive of how it would be done. But that's a remarkable thing to think about it, because it's Wigner, a great physicist, wrote an essay back in the 60s, I think, called The Unreasonable Effectiveness of Mathematics in the Physical Sciences. And by the unreasonable effectiveness is demonstrated by this discovery, because it really is a mathematical prediction. It's like we think there's a new fundamental particle that does the job of giving mass to the other particles. And this is how it does it, and this is how it behaves, and this is what it will look like, and this is what it will do. And then 50 years later, you build the biggest machine ever built, 16 miles in circumference. Most of it's in France, a bit of it's in Switzerland.
10,000 scientists, 150 countries.
You accelerate protons, the nuclei of hydrogen, around this thing at 99.999999% the speed of light. They go around the 16 miles 11,000 times a second. We can collide 600 million of them together every second to recreate the conditions that were present less than a billionth of a second after the universe began. Photograph it in the biggest digital cameras ever built. The one I work on called Atlas is 40 meters in diameter. Vast thing. 7,000 tons of digital camera in a cavern the side of St. Paul's Cathedral underneath the ground in Switzerland. And you find it. You find this thing that this guy, Peter Higgs, working with many other people, predicted to exist 50 years ago because he did some sums. And so it's real. So the universe does behave like that. There is a condensate in the vacuum. It is a Higgs condensate. It does give mass to the other particles. So it's a tremendous testament to the power of human reasoning, I think. And it means that we understand physics. It means that that's one of the important things about it. It means that our understanding of fundamental physics is not horribly wrong at the moment. It's good enough to predict something like that, which is a remarkable achievement.
That is mind-blowing. That is truly mind-blowing.
And do you know when Peter Higgs actually, the day that the discovery was announced at CERN, packed auditorium, and Peter was there, and a journalist went up to him afterwards, and just what I've said, this is what happened. This machine did it. He found this, and they said, "How do you feel, Professor Higgs?" And he said, "It's very nice to be right sometimes."
We're now in the centennial decade of the discovery of quantum physics back in the 1920s. And the whole 1920s was done before we discovered the neutron. That's crazy.
Yeah.
Let's get back to the fundamental particles.
Yeah.
So
then we discovered that the protons and neutrons are made of
quarks.
So they are, far as we can tell, point-like objects. So they're fundamental. They won't be, but as far as we can tell, they are experimentally.
So we have the photon, the electron,
let's
three quarks.
Take the matter particles. So the up and down quarks make up protons and neutrons. So a proton is 2 ups and a neutron is 2 downs.
And we have per energy stratum here, correct?
Well, so then we have this nice thing. So we have the electron, as you said, the up and down quark, and then the thing called the electron neutrino, which we just talked about.
Only 4 fundamental particles in anything we know or care about.
So we have 4 of them. Yep. That's it. And then we have
so I can construct you out of these particles.
Yes.
If I had the recipe.
Yes. But then, so we have 4 of them. So
okay.
That's it. There's 4 of them, and then the forces that mediate the interactions, right?
Okay.
And which we can also think of as being carried by particles, as we said.
Okay.
We have the photon,
the massless particles,
the electromagnetic force. We have the W and Z bosons, which do the weak nuclear force, and the gluons, which do the strong nuclear force and stick the quarks together.
Aptly named gluon.
The gluons,
yes.
yeah.
Okay.
And so that's it. It seems, except that there are 2 copies of those that are identical, except they're more massive. So there's the common strange quark and the mu neutrino,
That's nothing. That's the next level up.
They're more massive.
More okay.
So you have the Charman and the neutrino, and then which are the or sometimes called depending on how you want to do it, the quark, and then the tau neutrino, and that's as far as we can tell. So the
4, 8, 12 fundamental particles, and their antimatter counterparts.
Yeah, and then the counterparts. Okay. And so that we don't know why there are 3, and experimentally proven really with some very small caveats. Only 3 generations, only 3 families of these things. It looks like a periodic table. So remember, you go back to Mendeleev and the periodic table. How do you understand that pattern in the chemical properties of the elements? You understand it when you know that everything's made of atoms.
Yeah, I mean the chemist arranged it, but didn't have any understanding of it.
No,
quantum physics.
Well, you need to know the structure. You need to know that there's a nucleus, and there's hydrogen's got 1 electron, and helium's got 2, and carbon's
alchemy only gets you so far.
Yeah. So you understand chemistry. You understand the pattern when you understand the building blocks.
Okay.
So we don't know why that pattern is there, but it's clearly telling us about the building blocks or the underlying theory, which we don't know. So it's one of the great mysteries.
When we first started to point initially radio telescopes to Venus and then began to fly space probes past the planet, we found that Venus is a scorched world. This is a photograph from a Russian spacecraft called Venera 9, which landed in 1975. It found a world that it could barely survive. It only lasted for around an hour. It measured temperatures of 465 degrees Celsius on the surface. The atmospheric pressure is 90 times the atmospheric pressure on Earth. That means if you or I stood on Venus, we would be toasted and then squashed. And if that didn't do for us, we would be dissolved because clouds of Venus rain down sulfuric acid. So far from being an idyllic, beautiful bringer of peace, the goddess of love, Venus is the closest world to hell you could imagine. When we started peering through the clouds using radar, and we see a surface that is covered in volcanoes, far more volcanoes than any other planet in the solar system. What's interesting, though, is that it seems that, again, like Mars, Venus would have had water on the surface, may have been a habitable world, may even have given rise to life, may have been that paradise. But something went wrong on Venus. Those volcanoes pumped carbon dioxide, sulfur dioxide, greenhouse gases into the atmosphere. The cycles of the planet ran away with themselves. A runaway greenhouse effect heated the planet up and destroyed it, certainly as a habitable world. So I think the lesson of Venus is that planets are not eternal. A world that was once heaven can become hell. Venus, bringer of peace, becomes a requiem for a failed planet, and perhaps also a reflection on how rare places like Earth might be.